Okay, so I'd like to welcome Patrice for the next talk. Patrice has a PhD in cellular biology. He received that in 2012. He's worked in various core imaging facilities, including CR UK and the University of Bordeaux. And now he's the sales and application specialist at DRVision. So over to you, Patrice. Thank you.
Thanks for the introduction, nice introduction, and thank you as well for organizing this conference, this online conference. It's really an amazing opportunity to speak. Yeah, I mean, in that situation now, and yes, as well, you should be seeing my screen now, my slides, and yeah, I can start. So yeah, and thank you for inviting me to present Aivia software, which is software offered by DRVision Technologies, and which is an image analysis package of tools, which is AI powered, and I will come to that later in the presentation. And first, what I would like to do is to give a very quick introduction to what is DRVision company. So it's a company existing for more than 20 years now, and if I come back to the little background of this company, is that the people who started this company were owning Neopath from 1989. So, I mean, a long time ago, and they for 10 years, almost 10 years, they worked on designing an automated microscope to acquire some pap smear slides for automated acquisition and image analysis. And this is still a device which is sold right now, which is a big focal point device right now. And in 1999, they decided to switch to another company which would be more focused on the software part, which was S-Vision, and it was later on rebranded as DRVision Technologies in 2008. So James Lee is still the CEO and president of this company. And he hired in 2016 Luciano Lucas to work on a new package which would be named Aivia, and which would be more focused on delivering tools for the scientific community. In the past, they've been working on products, customized products that were delivered directly to industries or some labs, but here the goal in 2017, it was really to release something which was more broad, a broader package of tools which would be more flexible for the research field. So here really, that's what I wanted to depict, is that the goal was really to cover many state-of-the-art technologies and tools that could be available right now, and put that in a package so that people would not have to change software when they want to do the full work on their image analysis projects. And as you can see, from 2017, April 2017, with the first release of the first version of Aivia, we have been developing and implementing many different tools over the past 3 years, so 10 new versions. So just showing that we have a very dynamic development pipeline for this product, and we are really very happy to receive feedback from the scientific community to improve the tools that we provide to this community. So, coming back to the name, Aivia stands for Artificial Intelligence and Visualization for Image Analysis. So really showing the goal of bringing the artificial intelligence tools that we hear about in the past conferences, along with the image, let's say the more standard image analysis tools, on top of as well some rendering tools. And this is what would constitute the full package of Aivia. So a very quick reminder about some terms that we will use in the presentation here, and that you will hear in conferences as well, is that artificial intelligence stands for a very big group. And this big group corresponds to something which is about mimicking humans. And this can be something very simple. It can be that you have a weather forecast station that will answer about what is the weather forecast today. So nothing more. It will not analyze your images, right? So machine learning is a subgroup, as you can see, of this artificial intelligence big group. And here the goal is that this group of algorithms will learn from the input data or from specified information in the data, and then can define some specific rules for specific tasks. So for instance, you will have this in the web browser search engines. When you type something, you have some predefined results, and these predefined results come from what you typed before. So there was a learning process in that algorithm. And in that subgroup, which is the machine learning, then what you will see is a little one, which is a deep learning one. And deep learning stands for some subcategory of algorithms that are very, let's say, dedicated to more complex tasks, and that can really be more accurate than let's say the other algorithms for some tasks, for instance, for image analysis or for restoration of images. And the goal is really to be as accurate, or at least as great as humans, in the precision that we can get from these algorithms. And for instance, that's something that would happen when you have a live capture of with your smartphone of what is in front of it, and you would like to translate only the text, but not anything else that could resemble, that could look like some characters. For instance, the shape, the big O shape, should not be translated, only the word in it. So now, if I come back to Aivia, what we can find in the machine learning subgroup or category, which is excluding deep learning, we'll find the pixel classification. So pixel classification relies on the fact that you will pick for single pixels what is the environment information that could correspond to, for instance, intensities, but also shape information and morphology and texture. And you will use that information to classify these pixels and then get results. Like here, it's color coded for each class. And the one that you do not see, which is not output, is all the other pixels that are belonging to another class, which is not represented here as a result. And from that, we implemented in the software the ability to directly output segmented and split objects from that classification. So if I show a quick example, it looks like this. You will have the ability with pixel classification then to really have region identification on the left, for instance, getting, for instance, some information about an area, and use that region in further steps to quantify something within that region. Or you can directly count or segment some objects and get some information for each of them as well. So the last step that is possible with this pipeline is the fact that you can do the same as you would do with the pixels, the individual pixels. You can classify objects, meaning that, for instance, for a neuron, it starts to be very, very powerful because you can have some morphology information or intensity information about the soma, but also about all the branches and let's say the connectivity within these branches. So on top of this, what we offer in Aivia is as well the deep learning part. So you heard about it. And we offer segmentation applications, restoration, and also prediction, which means that you can predict some, let's say, organelles or subcompartments or compartments of the cells, for instance, like nuclei, from a transmitted image. So you do not have fluorescence image, and you would like to get some information from this transmitted image. But of course, for the training step, you will need this ground truth, the real result that you are expecting, and this would be the fluorescence image. So I can come back to that as well. Here with an example comparing machine learning and deep learning pipelines. So machine learning in Aivia corresponds to annotation tools that you would use to specify examples. So examples for a class, for instance, yellow class 1 is the object that I would like to have, and the red is everything else. So you can annotate the image, get a live preview in the software, and then train. And then the output of this training and application, so you would apply that to the full, let's say the full image, and you will get a result as a confidence map. And this confidence map is really simple. It's for each single class. So for instance, here for the yellow class, you will have pixels that are, intensity that are close to 0, which means it's not belonging to the class that you would like to have. And the white is 255. It's from 0 to 255. And 255 corresponds to the highest confidence in this pixel belongs to the class that you would like to have. But of course, this confidence map is not necessarily final map of interest, because you potentially want to quantify that and the individual cells, for instance. So you would need a segmentation tool, which is available in our software, that allows you to really identify separated cells and then get quantification out of it, either for intensity or for shape and morphology parameters. But as I said previously here, what you can do as well is to get some direct segmentation outputs and split object output from the classification training. So this is another step that is shortening the pipeline and goes faster to the result. On the other side, the deep learning tools that we provide, and for instance for segmentation, would happen that way in terms of use. You need some raw data, of course, and then what you will provide is a ground truth image, which is the result that you would like to have. And these pairs, these corresponding pairs are actually binary masks. So binary is like white is what you want, and black is what you do not want, like 0 and 1. And you will train a neural network with this, and then you will have some final train network that you can apply on a new image, and then from that new image you will get this confidence map. Again, as you see above, these confidence maps are not objects. Whenever you want to create objects, you need this segmentation tool again to be used. That's why it's important to have it ready, because then you can quantify the objects at the end. And of course, it looks a bit similar, but what is very different is the time it takes for these actions or these steps to happen. So even if we have a quite unique setup of our machine learning classification with the GPUs of the machine, that can happen for training and application, and it would be the same for deep learning here at the bottom. It means that even if it's like we are using the power of the machine as much as possible, the machine learning is more dedicated to some tasks that are that are focusing on a small set of images, or let's say tasks that are less complex. If you have let's say shapes and objects that are quite similar over the full data sets, the full list of images that you have to process, it's probably better to use machine learning. If you not succeed with machine learning, you can switch to deep learning and potentially use that power to get better results, but you would need to invest more time on the raw data and ground truth data set. So more examples to provide. It takes more time. It takes more time as well to train and apply. So it's really about how much power you would like to have in precision and, let's say, in robustness of your or flexibility of your let's say trained model to be working for all your images. So that's something that you can choose in Aivia. So the one thing which is very interesting from our last release is that we offer now Aivia Community software, which is a free software that you can re-download without any registration. And you can do some 3D rendering in it. You can export videos, but most importantly, you can do these two first steps of our machine learning pipeline. So why is it called community? It's because these two steps, we think these are some really important steps that your community of collaborators for yourself would need these tools to generate these examples annotations, and get the preview and train the model. So the algorithm of machine learning. So if they can do that with the free software, then they can collaborate with you in an easier way because they don't depend on you. So this is why we want to foster that community and collaboration effect with this free software. So of course, on top of this, and I already introduced that, we have segmentation tools, more classical segmentation tool in Aivia, but it's also about all the other tools that you would need for image analysis, related to image analysis. So if I go quickly through them, it would be, for instance, the fact that you can visualize big data, potentially interact with it, let's say, review it with virtual reality, and I have some editing tools as well in 3D. But it would be also to have 2D and 3D segmentation and tracking tools, and also some neuron tracing tools. We have a full list of tools in Aivia, which is very interesting, very dedicated to neuroscience here. And as you can see, there is this image in the middle, which is quite interesting, which is about tracking cell phase contrast images. So it's not a classical tool exactly, because it's relying on a machine learning tool which has been pre-trained. So you can also find in Aivia some tools that are dedicated to some tasks. For instance, this task, it has been pre-trained by us on standard images, and you have some tweaking sliders in the software to adjust to let's say the contrast of your image to the training set, and then you can really just apply this pipeline to your dataset without any further annotation or training. So if I then summarize about the pipeline, so of course in the software it's important to have the ability to load different types of images. Then you can define regions of interest, for instance, can be with machine learning or manually or semi-automatically. And then of course you have this processing at the bottom, processing step, which is usually very important. So this is something that you can do in the software with machine learning, deep learning, but also with Python, because we integrated a way to communicate with, to integrate Python libraries and functions very easily in very few steps. And on top of this, of course, you will have this ability to segment objects and batch apply this, review the results, and then at the end, and the most interesting thing is that you can use in a very straightforward way this output, this work of defining some objects as the deep learning input if you want to increase the power and the flexibility of your and robustness of your let's say pipeline of analysis. So this is something which is very important, because then it means that you do not need necessarily to start from scratch with annotations, like manual annotations. So I want to also to go quickly to the advantage of combining a machine learning, not necessarily deep learning, but already machine learning tools to other tools. For instance, here in that case, again, I take this example of a fluorescence image where you can output a confidence map. And out of this confidence map, you can do many other things afterwards, because it's an image. So it's a new image relating the morphology of, giving you information about the morphology of your objects. And then you can use that output to be an input for the tracking, or for filament tracing, or even for colocalization. And I have a quick example about this. If we take the image on the left, the image on the left, I'll just try to, maybe not the whiteboard now, but this noisy and 3D image on the left can be traced, of course, with our 3D automated neuron tracing tool in Aivia. But this is in blue. What you can see, it's really very partial. You cannot. It's the best I could have in the software, but it's not really good. But what you can do is in the software is to use machine learning pixel classification to get the third image, which is the output, the confidence map, but seen as 3D image, of course. And then from that, using the exact same parameters from the blue to the green, you can see here how much improvement with the exact same parameters I could have just because I performed some restoration with machine learning. So really, the take-home message is that machine learning is good, but it's not all about machine learning or deep learning. You can use the power of everything and really get some very nice results in little time. So I will finish with here the first conclusion is about the fact that DRVision is a company now with an extensive experience with image analysis and AI, and at the side of seeing that AI tools that are more accessible now for many people, and we want to help this ability of using AI tools. You see that Aivia software is really the package that can answer that demand, really offering this end-to-end solution with all many different standard tools and AI-powered tools. And very importantly, you don't have to restrict yourself about the applications. Really, it's broad. You can really apply that to many different fields, like even material science or medical imaging. And you potentially have seen some conferences about that. And I will finish with a second conclusion, that the fact that we have quite important R&D activity at DRVision, and I just want to show very quick, brief examples. For instance, we are working on improving how we can perform super resolution with deep learning models. Here, in the case of going from confocal to STED, and we can thank Ari Schroff for helping us setting this and giving us these images as examples, as real examples. Here, the first one is confocal, the second one is STED, so which would be the ground truth of the example, and we can restore with the third image. As you can see, we can restore the two channels that would correspond to some resolution that is close to STED resolution. And a second example is that we are working on trying to improve the fact that we could have a way to reduce the annotation steps for deep learning segmentation. So if we consider this pipeline here, if you take the example of the middle image, which is what we call domain A image. Let's assume that it has been previously trained for a model to recognize the boundary of the cells in this image. So it's the red model, which is the red model A, let's say A compatible model. But further, you will come with a domain B image, which is the one on the left, which is different. It can be different, slightly different resolution, slightly different contrast, and then it doesn't work anymore with a compatible model in red. So you would need another model, but a strategy, or you would need to generate annotations for it. So one strategy is to use what we call domain transfer, or what is called domain transfer, and use a deep learning model that is able to convert the B image to the A image, and then you can apply your previous red model without generating any new annotation. So this is something that we are really looking forward to try on a broader range to see how it works well or not. And so I have a quick slide here to thank all our R&D collaborators in different institutes in the US. And also I would like to thank the Aivia team, my colleagues, because it's a growing team, a very growing team now. And it's a majority of developers, and they are really working hard on making Aivia a better tool for scientists in general. So thank you, and I think I will just quickly answer one question, which was first asked, by someone about connectivity of Aivia. That's so I have a very quick slide about this, which is that Aivia is something that you can use on your local machine. So I guess the question is about how we can use machine learning, deep learning with your own storage or potentially with other storage or other servers. And that's something that can potentially be feasible. So you have Aivia at the bottom that can run on your local machine, but you can as well have in the software a connectivity with deep learning Google Cloud Platform option or solution. That is something that you would that is possible with the contract with them, that we take care. And also there is another opportunity which is on the right, which is on top right, which is Aivia Web, something we are pre-releasing now, which is the ability to have Aivia working on a web server that you can access from your web browser on any computer. So your computer can be low end, and you will benefit from this high-end machine. And this is something we are offering for free for the confinement time in April. So if you are interested, you can contact us about that. So yeah, so that's to answer this question. And I think, yeah, that's. Yeah.
Okay, thank you very much, Patrice. That was a really good talk. I must recommend people have a look at the Aivia software because the interface is really beautiful as well. And it's very simple to pick up, even though it's very powerful software. It's very easy to get started. Patrice, I understand that you've got some workshops coming up over the next few weeks for us. Can you tell us a bit more about those?
Yes, that's right. The goal is to either use the power of Aivia Web or use the fact that we can do some online, let's say, conferencing and get some feedback from users directly. So really the goal of these workshops is really to have some hands-on sessions for people. So we would have a first introduction to the tools, picking each time, so each week it would be a different example. For instance, it can be how I could perform 3D segmentation with this kind of images. And then people will have access to one personal session of Aivia Web to try that on their own, what is it called, the hands-on session, really. So we are looking forward to, let's say, try to use that, in that particular situation, try to that power of, we have some access to a computing server, and people can try that because it's virtual machines, and we can really set different sessions for each of them. So we will try to do that in the next weeks.
That sounds great. And can people sign up on your webpage?
Yeah, definitely. They can visit the DRVisiontechnologies.com website. They will find all the links for that. Yeah, that's right.
Perfect. Right. Thank you very much. I think we'll move on there. So thank you very much, Patrice, and we'll move on to our next speaker.
Yeah.
Cheers. Thank you. Bye.
Bye.
Welcome back, everyone, after this technical issue. So I don't know if Mark Nail presented me or not, so I will present myself. My name is Ali Ahmad. I am a PhD student working at Creatis Laboratory of INSA de Lyon in collaboration with Laris Laboratory of University of Angers under the supervision of Carole Frandel and David Rousseau. Before I start, I would like to thank the organizers for giving me the opportunity to give the talk entitled Adapting Machine Learning Feature Spaces with Microscopy Image Resolution for Single-Cell Classification. This study that I will show you is one of the studies that I realized during my PhD in the framework of ProChip European project. During the previous presentation, they presented and they introduced machine learning and deep learning very well. Here, I will focus during this quick introduction, to talk about the main difference between machine learning and deep learning. Sure, they are both used to resolve some problematics such as segmentation, detection, or regression, and they are both based on the same principle, that is mainly extract features and train a model. So, what is the key difference between machine learning and deep learning? In machine learning, the user has to analyze his image manually and then to extract or to select the best feature spaces that characterize the information inside his images, his data, to have the best output. But in opposite, in deep learning, everything, this action is automatically achieved by the model itself, where he adapts the filters that extract the features. He adapts the weight of these filters to have the best output. So now let's focus just on machine learning in this the first part of this presentation. Let's focus on machine learning only, and let's talk about how we can adapt the feature spaces if we have an application in microscopy and the informational task, or our task is to do the classification of single cells inside. And since we are limited on the size of data, the size of real data, the best way to do this kind of such studies is to generate synthetic data and use them to apply this kind of studies. So our synthetic data are generated with a pipeline that is divided in 4 blocks. First, we have to generate the fluorescent markers inside the space in the image, and then we have to add the experimental condition of the microscope. Once we have the image, we have to start extracting the best feature spaces after to prepare them to the training stage of the classifier, and finally we will have the classification of the cells between healthy and cancerous cells. Now, several biological studies that found that there are different or during the move of the cells from state to another, there are this moving or this path from healthy to cancerous, for example, is demarcated by modification of the special organization of the DNA. So for us to do this, to do the simulation of this synthetic data, we're based on 2 kinds of studies or 2 kinds of special organization differences. The first one is based on density differences, and the other one in distribution differences. For that, we generate using random distribution 2 kinds of cells or 2 classes of cells, C1 for healthy and C2 for cancerous, and we create differences in the density of the generation of the fluorescent markers. But and the other one, or the other type of distribution or of the studies, we generate the fluorescent markers in clustered way. So we will have the distribution differences if we compare with one of the class of cells of the cells C1. So now, in the following of this presentation, we'll do the classification based on 2 kinds of special organization. The first one is density differences. We classify C1 and C2. And the other one is classification based on distribution differences. We use C1, the healthy class cells, and C3. Once we have this generated fluorescent markers, we have this object. Now we have to introduce or to add the experimental condition of the microscope to the image. To do that, we simply simulate the PSF, the point split function of the microscope, with a simple Gaussian that we can modify the size of this Gaussian window to have several types of microscopic resolution. For example, if we are in low, if we have a small size of this kernel Gaussian, we are in super resolved microscopy, and when the size of this Gaussian denoted by sigma PSF become higher, we go more to sub-resolved microscopy. Just for information, okay, it seems that this is not the good version of the presentation, but I will continue. Just I want to say that now that super-resolved microscopy have higher cost than sub-resolved microscopy. The cost could be in the price and the acquisition time, and in the optical system complexity. So it's good to know now, or to find a way to do the classification of the cells and to find if it is really necessary to have a super-resolved microscopy to achieve such a task. Now, once we have the generated or the synthetic image, we have to analyze this image to select the best feature spaces to characterize the data inside the image. To do that, we have just to take a look to our generated data. If we take a look to super resolved microscopy, for example, we found like point cloud behavior. But when we go to sub-resolved microscopy, we have like textural behavior. So it's a good point to start. So we can start first by extracting features based on point cloud, and the other one based on textural behavior. To do that, for point cloud or point list feature spaces, they exist a lot of features or a lot of feature spaces that characterize the point cloud distribution. We selected, or we worked with two kinds of these features. The first one is distance distribution analysis, and the other one is replace K function. Before we can apply this kind of analysis, we have first to localize. The fluorescent markers inside this image. So to do that, we used unsupervised particle localization imagery plugin. We localize the fluorescent markers inside the image with different resolution, and then we calculate three kinds of distances to do the distance distribution analysis. The first distance is distance between the markers. The other one, distance of the markers to the mean, and the third one is distances of the two nearest markers. Once we have these three distances distributions, we can feed them with real probability distribution. So we feed them with Rayleigh distribution, exponential distribution, and generalized extreme value. And after that, we took these five statistical parameter of this probability distribution as features. Let's pass now to the other method used to characterize point cloud aspect. We used here the replace K function that is usually used used in microscopy, in super resolved microscopy, to describe how markers or fluorescent markers occurs over a given area. Usually this area of interest is taken as the circle of radius r. When we change, or when we increase the radius r, we will have such a curve that is presented in this slide, replay K function of this radius. We present here the brute these curves for the raw data generated, raw data for the cells C1, C2, and C3. If you have to analyze these curves, we can extract 5 types of features from them. We consider first the maximum value of K function, and then the corresponding radius, as the features. We can take the maximum gradient and the minimum gradient and the correlation between the curve, K function curve, and the radius axis. Now we have 5 features for distance distribution and 5 features for replace K function as pointillist approach. Let's pass now to the texture characterization of the image. There are a lot of methods that characterize texture inside a given image. So we used in our study here three methods, 3 standard methods used usually to characterize the texture are the autocorrelation, the gray level co-occurrence matrix, and the local binary pattern. I will pass quickly on them. So for autocorrelation, we can calculate the autocorrelation function of an image by a special Fourier transform, and then we can take the X profile as it showed here. I will try to. So we can take this profile, and we will have for the 3 classes such graphs or such X line out profile. From this, we can extract some features also. So if we take the maximum value of autocorrelation function, we can take the full width half maximum, and then we can calculate also. Here is not too much clear, but here we have kind of variation. So we can calculate the maximum gradient, minimum gradient, and the variance after removing the peak from this profile. The other method used, I talked about gray level co-occurrence matrix that is usually a matrix of 8 by 8 pixels that represent the frequency of occurrence of pairs of pixels inside the gray level image. For example, here the pairs of pixels we can take 1 by 1 separated by distance d taken as 1. We have only one, this pair it's repeated only one time, so we put 1 in the corresponding place. Another example, we have 1 and 2 values, it's repeated 2 times, and we put 2 in the corresponding place, and we complete to fill this matrix in the same way. Finally, we will have a matrix of 8 by 8 bits, and we can calculate for 14 early coefficients that are second-order statistics from this matrix, that they are, for example, the similarity, entropy, the correlation, for example, the variance, and others. The third textual method that we used to characterize the texture here, we used the local binary pattern. During the local binary pattern, we divide the image in small region, and then each 8 pixel, 8 neighbors, are compared with the value of the central pixel. So if they are higher than this value, we put 1, and if they are lower, we put 0. Finally, we'll have for each region a binary code corresponding to a decimal number. The frequency of occurrence of these decimal numbers in all the image, in all the LBP map, they will be considered as features. Here, the frequency is represented in histogram. The value of the bins inside this histogram are considered as features. And we can calculate, we calculated for our image 59 features per image. Once we have all these extracted features, we have to select the best classifier to do the training and classification. In our study here, we tested several classifiers that exist using classification learner MATLAB application. Here we tested support vector machine, decision tree, logical regression, and KNN. And we took the best one that gives the higher result for specific specific PSF value. So we select the SVM as an optimal classifier, and after that, to do the training, we have to reduce all the feature spaces to have the same size, the same dimension. So applied principal component analysis to reduce the feature spaces of gray level of co-occurrence matrix and local binary pattern to 5. And just for information, we created, or the training data sets for this study was 2,000 image for each class for each PSF size, and the testing data set was 250 for each class for each PSF size. We arrive now to show the results of this study on synthetic data. I will just discuss this result globally. So on the left, we have the density differences based classification, and the right distribution differences based classification. To analyze them or to interpret them, the red curves on the left and the blue curves on the right corresponding to the textural approach, and they overcome the other feature spaces that belong to the pointillist approach, the black and the pink one. It's in general that we found testing for various PSF size, and we found that the pointillist approach are only efficient when we are in super resolved microscopy, and this could be related to the efficiency or the capacity of the localization of point. If we localize the point with a good precision, we will have a good classification. If not, the classification will be something like randomly, because we have a lot of error, we have a lot of parasites. Finally, we can say that we can select from the same type of the feature spaces one of the most that gives the higher result and the most stable result. That is the autocorrelation, because we can see that the result, the performance of classification are stable over all the PSF, whatever is the PSF size. This was concerning the machine learning test. Now, what about deep learning test? Oh, okay. I will test here in deep learning, and then I will back to the validation with real data, because it's not the correct version of the slides. So for deep learning, we tested the same classification task applied to detect the density differences between classes C1 and C2 using conventional neural network. We applied this in optimized architecture that constitute of 3 convolutional layers, and we have the output 2 neurons corresponding to the healthy and cancerous cells. The result of this test applied to synthetic data, we found it that we have low results for all for all the PSF size. So what are the reason of this? What are the reason of this this drop in performance for deep learning? Because usually we know that deep learning gives the best results over among the machine learning classifiers that could be used. But the reason here of these low results could be related to the first point, that we have no context information. We applied this classification based on the category of cells that the difference between them are based in a small density differential that is around 0.03. So each time we have the convolution layer, we are losing this information, and this in the end we will not have the good resolution or the good contrast between parameters to have the best classification result. And the other reason is that we have small amount of data, because when using deep learning, we should have at least for classification, sure, we should have at least 10 power 4 images for each class to have the best performance. I will back now to show the results applied to real data sets. The machine learning algorithm was applied to data set of Aurox clarity images. We have 1,000 healthy cells and around 1,000 cancerous cells. The resolution of these images are like conventional resolution, so it's the sub-result microscopy, and the result that we have for feature spaces of machine learning is very close to the one that we have in synthetic data, where we have the autocorrelation feature space have the most or the higher performance. And here for the quantitative approach, the performance is really affected by the capacity of unlock to localize correctly the points. Finally, we'll come to the conclusion after all these tests. So we realized the study that to select the best feature space depending on the microscopy image resolution, and we found that textural approach can be used for whatever is the resolution of the image, can be used to test to classify or to detect some differences between based on density or in distribution. And we found that for quantitative approach, it's only effective when we apply the super resolved microscopy. And the third point that is very important for such classification task, if we are doing the classification between healthy and unhealthy cells based on this kind of special organization differences, usually we think that we need to have super resolved image and localize the points correctly to have good performance or to realize or to achieve this kind of test. But in this study, we showed that we can, even if we have low resolution microscopy images, we can apply textural approach and we can have a good performance of classification between the two classes of cells that are based in special organization differences. Finally, between machine learning and deep learning, which one we have to use, the choice of machine learning or deep learning should depend on the type of our data and on the size of the data that we have to use to train our model. So, at the end, I want to thank you for your attention. I'm sorry if I exceed the time. Okay, and I'm ready to answer the questions.
Okay, thank you, Ali. Thanks for coping with our technical details. Let's hope Webinar Jam isn't run by a neural network. Perhaps we can. I think we've got one question here. Laurent Thomas asked, the classification was for the full image or cell by cell?
Yeah, it's a single cell classification. We classify cell by cell.
And I was wondering, can you give us an idea of how long the code takes to run on your data set? So there's a training stage and a.
The training stage is very high. Is very high. maybe if I can share the screen, I can show a table.
Okay.
I can show you the computational time of each feature space. Yes. Now, maybe I'm not able to share the screen with you.
Okay.
Yes, turn on share. Yes,
Okay.
I can do it. Maybe.
So you can give us a short idea on is it hours
Yes.
or minutes or?
Yes. So the thing that each kind of feature spaces have his competition time. So we found that for GLCM feature spaces, the lowest time we took, it's very quick. But after that we have the autocorrelation, and the lowest time for computing the feature spaces are for distance distribution and replace car function. A lot of time to calculate the squirrel feature.
Okay. Okay, right. Well, great. Thanks again, Ali. Fortunately, despite our technical difficulties, we haven't particularly overrun in time yet because our next speaker is unable to make it today. I think he's doing some interesting work with Philippa, and they may well be presenting some of that in a webinar later in the spring. So if I can go on and introduce the speaker after that, who's Professor Michelle Peckham. Michelle is based in the University of Leeds. She works on molecular motors, does a lot of super resolution microscopy and analysis of super resolution microscopy data. She's the former president of the Royal Microscopical Society, and today she's going to be talking to us about about finding patterns in super resolution data. Okay, Michelle. So I think you're online now. Maybe Lee can put up your slides, or you can share your screen and join us with the microphone and camera.
Yeah, I can just put up the slides for you.
Okay, Michelle, we can't hear anything at the moment. If you can click the microphone.
There we go.
That's it.
Right, thank you. I've never done one of these before. So this has been quite interesting because, of course, as you'll hear from Peter later, the RMS is kind of thinking about whether or not we might want to do these types of things if we can't meet in person. So it's been a very interesting experience seeing everybody talk. There's been a nice selection of talks this morning. Thank you for holding on for me. So I'm going to talk about something that's really Alistair Curd's baby. So he's been developing this way of identifying patterns of protein organization for some time now. You can see there's a lot of other people involved, and there are even more people involved as I go on through the talk. So I'm a biologist. I'm interested in how proteins are organized in cells. Lots of proteins are organized in some way. Can we actually detect this by super resolution techniques? But not only can we actually see a super resolution image, but can we actually see something about how the proteins are organized? And in quite detail. So we have very high resolution data from super resolution images, and really what we want to do is quantify them properly. So that's an example of nuclear pore, and we've used this data that James Rees has kindly given us as one of our test data sets, and obviously you can see there's a nice pattern of organization of proteins in the nuclear pore there. So how do we find the patterns? So there's been quite a bit of work in this area already. I think probably nuclear pore has been worked on quite a bit. So this is an early example from this paper in Science, where people have taken super resolution images, seen that there is this pattern, taken the different particles, the two different nuclear pores, and that's after doing some quality control to pick the best nuclear pores, aligning them and summing them. And of course, the problem is that because of, although this is nice super resolution data, there isn't quite enough detail to do a really nice alignment, so you end up with a ring. But you can measure the distance from the center of the ring, and you can see what that is, but you're not getting all of the information that perhaps you could get out. That was being followed up with more work. So again, this is using a template, so a structural template. You can see here are the nuclear pores being picked, and here's the sort of final images. But of course, that's using a template, which could potentially give you a little bit of bias, even though, of course, for the nuclear pore, we have a pretty good idea of what the symmetry is from EM data and so on. This is a reference method. This is based on doing the kinds of things that, so I also do a bit of cryo-EM, and in cryo-EM or negative stain EM, what we do is we take lots and lots of particles, and then we classify them into particles that look the most similar to each other. And this is exactly the same technique that's used in this paper published in PNAS. So you can see how the different classes look, and you can do some averaging, just as we might do in an EM experiment. And in fact, we've actually tried this type of approach ourselves. Then a couple more examples. This is from Sulio and Mandy's group, again using this sort of image classification type of idea. This is now using centrioles, and centrioles are a bit trickier because, unlike nuclear pores, they're not flat. They're quite often at an angle or distorted. So you also have that additional problem to deal with. But again, you can see you end up with something that looks pretty much like a ring-like structure and doesn't give you a lot of molecular detail. And then I just wanted to mention this last one that was published quite recently, which is using a Fourier transform-based method, but it's also doing some sort of manipulation of these rings to make them more ring-like when they're not ring-like, so circularizing them before doing this transform. Okay, so there are a number of things out there, but none of them really do what we quite want. Oh, I've forgotten this one. This is another method, again, which is using a cross-correlation type of method. And again, rotating the objects before you align them. So those approaches then require perhaps all sorts of different things. So perhaps you might have to align the images before you analyze them. You might have to pre-select your best data sets. Some of them use Fourier transformation, some of them don't. Most of them, if not all of them, use some sort of segmentation. So you're actually selecting your nuclear pores or selecting your centrioles in order to analyze your data. And they also mostly require that you label your structures with quite a high density, which isn't always possible when you, isn't always possible when you're trying to do, especially more the 3D type of super resolution. So we wanted to develop a technique where you could use your entire field of view, you didn't have to segment, and you could deal with this low labeling levels that you quite often get in super res. So this is the overall strategy. It's pretty straightforward and simple. When you do any sort of super resolution imaging for the single molecule approach, you end up with a table of XYZ coordinates. So what you can do is take those XYZ coordinates and measure the distance between them. And we call that the relative position. And then we can replot that relative position as a density plot to analyze their distribution. And then what we have to do is try and work out what model best fits that distribution. So we have to generate some model RPD plots. So we generate those separately based on a best guess model. And then we compare our model plot to our experimental distribution. And then we use some statistics to estimate which model fits the best. And we use something called a K-key information criterion to do that. And that's a strategy used quite often in spatial statistics. A lot of ecologists use this, for example. And then we use that to find the best model that describes the data. It may not be the true model, it's the best model that we can find. So that we've got the software. It's all written in Python. It's available. It's freely available. There's the link there if you want to look at it. And we've got a paper up on bioRxiv to explain how the method works. Okay, so this is the biologist thought experiment. So this is not, this is a bit simple, a simple way of doing it. So let's say we've got some sort of organization, and if we just think about the 2D case here, and we're measuring the distances between these localizations, and we can say, well, this distance occurs twice, this distance occurs twice, this distance occurs once, and we can plot the distribution of those three distributions. There's going to be some sort of Gaussian spread to those, as you might imagine, so that's what it might look like. If you go into 3D, it gets a bit more complicated, but I've tried to sort of estimate what a plot might look like there in my head. So it's a very simplistic way of looking at it, but I hope it gives you the general idea, particularly if you're a biologist like me. All right, so I'm going to show you how it works in practice. So we actually use a Python-based visualizer to see the software. So we get our XYZ coordinates, and this is what we can actually see for ourselves. So this is the nuclear pore data. We can do the scatter plots. Here's the whole field of view. That's just a zoomed in part, just so you can see that each of these spots here is actually a ring. And then you can also do the scatter plot instead, of course, as well, of course. But we are analyzing that relative precision density in the whole field of view. Okay, so we do that. We take the whole field of view, we take the XYZ coordinates, we calculate our relative position density, and then we have to plot that. And of course, when we plot it, what's most sensible to do is to use the dimensions of the structure that we think has got the pattern. So in other words, for something like a nuclear pore, it's about 200 in X and Y. So we're just considering the XY at the moment, even though we have the 3D data set in our new RPD table. We're just looking at the moment at the XY pattern. So we obviously don't want to plot more than that, because then we start to take recent nuclear pores and so on, and then which we're not interested in. We're just interested in what the pattern is in a single pore. And in fact, that sort of slight raise there is to do with background probably starting to pick up adjacent molecules and so on. But we can see that there are some peaks here, for example. So what we need to do now is interpret those. So here is our best guess model, in fact, and we can interpret this in the following way. So first of all, there's some localization precision element, because although we measure where a single molecule is, we have some uncertainty about exactly where it is. Second of all, there are a couple of instances of this molecule in a single position in the ring. So I put 3 crosses here. So that's this distribution here. Then there are these distances around the ring. So you can see the various peaks here, with E being smaller because there's only one repeat of those. And then if you sum all of those up, you can see that you get this total model RPD. So that's for an 8-fold ring, which we already know from EM that the nuclear pore has an 8-fold ring. But if we didn't know, we could do all sorts of plots. So it's 5-fold symmetry, 6-fold symmetry, and so on. And you can see all the different plots here. These are the sum RPD plots. And then you can compare those to the actual experimental data, and then you can calculate this corrected Okeke criterion. And then you can weight it. So the weighting of this is all summing up to 1, and the highest number is the most likely model. So our most likely model is an 8-fold symmetry, and it's about 4-fold likely than the next one, which is a 9-fold symmetry. Okay. So that also, you can use that criteria then to fit some sort of error to your curve. So you can see in the inset there, I've got an error on the curve. And of course, now we know it's an 8-fold symmetrical ring, and we know something about that from the RPD and the Okeke fit criterion and so on. We can infer a structure, and that structure now has the right sort of diameter and compared to what we know from EM. But we've actually got some structure, so it's not just a ring now, it is actually some sort of structure, inferred structure. We can do the same in the Z direction. So this is exactly the same in the Z direction. It's mostly that single peak there from the distance between the two layers. That's our prediction. That's the actual separation from EM that we know about. And you can see we've got a good agreement there. Actually, just before I leave that, the original, this plot is done using not doing any sort of depth discrimination at all. What we can do is replot this RPD plot, but restrict the Z distance that we're looking at. Because in fact, there are two rings on top of each other, and they're not exactly on top of each other. They're slightly out of alignment, if you like. But if we restrict that plot in the Z direction and repeat our analysis, we actually get a much greater AKK confidence for the eightfold symmetry. So we can go back and reanalyze the data, and once we know more about its structure, we can go and refine the model and go back and plot our data in a different way and become more confident about it. Okay, so the whole reason why we developed this technique in the first place was to look at muscle Z disks, which is something I'm interested in as a biologist. And Z disks are interesting because this is one of our images from the storm system, and it's shown here that normally in confocal microscopy this would just be a line, and because of the way that the localizations have been binned in this image, you can see it's still just a line. But that line is about 100 nanometers wide, so it's below our resolution limit normally, and what we want to know is how proteins within that Z disk are organized. So one of the ones that proteins in the Z disk, of which there are about 50 that we know most about, is alpha-actinin 2, and it's a dimer that cross-links the actin filaments. So here are the actin filaments in red, here's the actin in green, actinin in green, and here is the actin binding domain in the dark green there. And the actin binding domain is 2 calpain homology domains, and we have something called an affimer, which is a non-antibody binding protein that recognizes that affimer. And this is really good for super resolution because it's a really small, you can see it's about 2 nanometers, and we can put a specific one dye label on it and image it at low density using 3D storm. So we don't have such a big linkage error. So here are some 3D plots of the data. This was a movie, but because I've uploaded it, it's no longer a movie. But here is a sum of projection of that. And you can see there is some sort of structure in here. And we have got some 3D information in there. Okay, so if we do our RPD analysis on that, we can see that if we go along this axis here, so from one side of the Z disk to the other, and what we do when we do this plot is we restrict, so we don't plot all of the information in Z, we restrict it to about 10 nanometers, which is just really looking at around one actin filament as you go from one side of the Z disk to the other. Here is our histogram in grey, and here is the model RPD that we fitted to that with the error. And that's consistent with a spacing between these actin binding sites of the actinin molecule of about 18 nanometers, which is actually very close to what it has been shown to be by EM. Where this falls down is actually looking in Z. So if we're looking to face onto the Z disk now rather than through the Z disk, there's quite a lot of discontinuity in the lattice. And so if we try and find a pattern within that lattice, we just get a straight line. So we're not able to pick out a pattern if we're looking face onto the Z disk, but we can pick out a pattern as we go from one side to the other. So where you haven't really got a clear pattern, we don't find a clear pattern. So we've got some other examples here. This is some data very kindly provided to us by Ralph Jungmann's group, where they made some DNA origami structures for us and imaged them and didn't tell us what they were, and we had to work it out completely blind, just to see whether or not, as an experiment, whether we could take a structure where we didn't know what the actual organization was, whether we could work it out from first principles. So, of course, we know something about DNA origamis and what they're likely to be. So Alistair constructed some models with various different patterns, and then created these model RPD plots, and eventually was able to work out that this was the underlying structure. And when we went back to the Ullman group and said, this is what we think it is, they said, yes, that's what it is. Result. That was good. And then finally, we've also been working with Kristen Sieben and Suliana Manley. Now, this is the tricky centriole problem, where centrioles, there aren't very many of them per cell, of course, unlike the nuclear pores. There's one or two. They do have a variety of orientation. So the data that we were given has already been filtered so that we're just looking at these top views with this more consistent orientation. And when we try and analyze those without doing any processing at all, we just get this single peak here. And that pretty much looks like that ring light thing I was showing you before. But what we can do is we can filter, use the purple algorithm to filter the data so that at least two of the peaks around the rings have an uncertainty in terms of actually being able to find these peaks. And then when we do that, we can actually filter this data set so that it then looks a little bit more like this, and then we can plot an RPD, and then when we combine all of that data or reconstruct it, we can see something that's got a bit more detail in it. So, so purple isn't just for finding patterns, it might also be useful for filtering your data and trying to help you pick the best particles. And we've got some other applications that we could use purple for as well. So that's pretty much all I have to tell you about. I think it's quite a nice, for me as a biologist, it's quite a nice, simple approach. It's quite simple to find your RPDs and plot them. The Akeki information criterion is quite a nice, robust statistical approach for finding the model that fits best. We've been using this approach for, as you can see, for lots of different applications. And certainly, we think for our storm data, we've got quite low labeling densities of about 1% or so. So as long as you can collect enough field of views, you can, of course, accumulate as many field of views as you want, because all we're looking at is the relative position density. So we can just keep collecting data. And as long as we have enough data, we can find these positions within the data. So I think that's it. And I'd obviously like to thank everybody who contributed to this. All their names have been in there as I've gone along. I'm happy to take any questions.
Okay, thank you very much, Michelle. There's been a number of questions come up already on the chat. Ingmar Schoen asks, for the NPC, does your model also account for labeling inaccuracy, i.e. that the dye is offset from the epitope in different directions? And is that incorporated?
I think that will come in that first peak in the.
So that's the localization precision peak. Yeah. So I think he's spotted that himself. Francesca Pinton asks, I missed what kind of input data you used. I'm guessing.
So the input data is when you do your single molecule analysis. So when you've got your storm or your palm data, and you find all your particles, you end up with an XYZ table, because that's what all single molecule localization approaches do. So it's just that XYZ table that comes out of, so if you did thunderstorm or any of the other SMM approaches, you end up with an XYZ table, and that's what we start with.
Okay. Gillian Dixon wants to know how long the processing portion takes. Is it hours or days? Is it longer or shorter than it takes to take the data in the first place?
So I've it's actually pretty quick. So I'm the test subject. So I've run it on my Mac. So I just have a standard Mac, and I've run the analysis on the nuclear pore data, and I'm a bit faster than a PC. I think it took me about 5 minutes. Well, so it's
probably quicker than taking the data in the first place, then, isn't it?
Yeah, I mean, it's pretty quick, actually. It's not hours or days. I mean, it partly depends, like everything, it will depend on the size of your data set. But certainly, I've run the nuclear pore data. I've done an analysis on that with, I think it was about 30,000 localizations in that, and it took a few minutes.
Okay. Is it possible, do you think, to use this kind of analysis, RPD analysis, in other super resolution data, so STED or SIM data?
Yes. Absolutely, yes, because it's, I mean, the basic principles are exactly the same. It's just looking for patterns in any type of data. So as long as you've got some sort of XYZ format for your data, or even just XY if you're just doing XY.
I suppose STED or SIM don't usually come out with a spreadsheet as their answer, though. They unlike localization data, it naturally comes out as XYZ coordinates.
So we have done a little bit with STED data in terms of actually a slightly different application, which is looking at co-localization. So you can get XYZ data out of that by doing some processing and then comparing your XYZ. So this is what we did for the localization. So the co-localization sort of approach. So you can always get XYZ data out of your images because you know where your pixels are. So it's just another processing step in there, isn't there?
Yeah. Okay. Cohen Martins asks, how does the sample drift influence the RPD measurements?
Well, of course, what we like to think is we correct for as much of the drift as we can. I mean, again, it will get wrapped up into some of the error that's in the RPD fits. Like anything, it will get wrapped up in the error in some way. In our lab, we have drift correction in action while we collect the data, and then we do drift correction using a fiducial afterwards to try and minimize that. Yeah. So we don't tend to worry about it too much. But obviously, if things drift in space, in time, they will end up sort of blurring your results.
So do you tend to use a home-built system, or are you using a commercial?
Yes, so we've got a home-built system. So we have it's based on one that Harry Schroff built originally. But it's also, it's the astigmatism type of approach.
Right, okay.
Yeah.
Okay. Ingmar Schoen's got another question. Is the sequence of your ACTN2 Aifia known, or is it commercially available?
The tricky kind of worms. So Aifias are a bit of a tricksy thing for us. So we know what the sequence is. We haven't published it yet. The sequence will become available because once the crystal structure is available, because we have a crystal structure for the complex, then you'll be able to find the sequence in the crystal structure. The Aifias are we make those at Leeds. There's a screening facility at Leeds, but there's also a commercial company, and we keep talking to the commercial company about how trying to make the ones we make for research more freely available. If you want it, you just write to me and I can probably organise getting it sent to you. You might have to sign an MTA like we used to do in the old days, but we're trying to make that a bit easier, but we haven't quite succeeded yet. But we do know what the sequence is.
Okay. Okay, I think we've probably run to the end of our questions there. So I'd like to thank Michelle again for a great talk.
Thank you very much for the experience.
That's all right. It's been an experience for us all. Yeah, and Lee and I were both thrown off at the same time earlier on. So next we've got Mary Valda, who's she's did a PhD at Friedrich Schiller University and a postdoc in Berlin, but now is based at the Station Biologique de Roscoff. She's studying biodiversity and symbiosis of marine plankton. So hopefully she's going to come up with some really great microscopy images for us to have a look at. And the title of her talk is Automated High Throughput Imaging for the Complexity of Marine Plankton.
Hello everyone from the shores of Brittany in France, and first of all, many thanks to the organizers. It's a wonderful scientific exchange in these times of confinement. The project I will hopefully present to you in a minute shows an application of AI for microscopy image analysis. And frankly, I think the project wouldn't really be possible without these tools. I'm using automated microscopy and taxonomic predictions to study marine plankton, eukaryotic marine microplankton to be more precise. So maybe I will start with a short introduction of what plankton actually is, and some of the particular challenges of this project. So plankton contains various organisms, viruses, eukaryotes, prokaryotes. So it's really a diverse collection of tiny organisms that float in the water and are not able to swim by themselves against the current. Plankton plays an important role in the ocean's carbon cycle. In fact, 50% of the world's oxygen is produced from photosynthesis of phytoplankton. It represents the bottom levels of the marine food web. So it's kind of important for life on Earth, and you can see why many labs in the world are studying it at different scales. So you could study plankton on the genetic level, on different organisms, on the community level, or even entire ecosystems. Now, can I move forward? Hey, great. Okay. Then I won't touch anything and just continue from here. So, yeah, the first question was, why do we want to image plankton? And I already showed you we can study it across different scales. One of the standard tools to study plankton at the genetic level are metabarcoding and metagenetic investigations. And in fact, recent biodiversity surveys of the world's oceans with these genetic tools have revealed that there's a large unknown diversity in microbial eukaryotes, which remains to be described. However, for an accurate taxonomic classification, a lot of the morphological data of these is actually missing. Additionally, many planktonic organisms live in intimate relationships, and these are not easy to distinguish from their sequences. So microscopy actually offers us a powerful tool to study both their morphology and also their interactions. Hence, there is a great interest in developing systems that can identify and quantify planktonic organisms in water. The predominant imaging techniques are still manual imaging and counting, or flow cytometry-based imaging methods. I showed you two examples here, the flow cytobot and the FlowCam. And while these in-flow imaging systems offer a lot of advantages, in particular when it comes to speed, they are quite limited in the morphological details you can get from it, and hence also the taxonomic classification performance you could achieve with these. So to push these current limits of image-based identification, we are here using an imaging approach that is based on confocal microscopy, which allows us to look at three-dimensional structures and finer morphological details, and thereby achieve a more reliable image classification. So as I previously mentioned, many planktonic organisms actually live in intimate relationships. So they're not too much into social distancing. Here you always see coccolithophore associated with a diatom. And you can see in the middle two images, the addition of a fluorescence readout already gives us more chemical contrast in the images. And while the spatial resolution might be best in the EM, actually I can use my pointer now, that's wonderful. In the EM image on the right, sample preparation for EM typically requires dehydration of the sample, which again then leads to a loss of morphology. However, the biggest advantage of using confocal for these kind of studies is their optical sectioning capability, and hence the 3D capabilities. So first of all, this enables us to achieve a better estimation of the biomass of these cells. And it also allows us to actually see inside of cells and thus detect symbiotic interactions. Of course, also other optical sectioning methods would be feasible. So we're also looking into spinning disk confocal microscopy or even structured illumination microscopy. But for now, it's based on scanning confocal microscopy. What's so difficult about imaging plankton? Well, first of all, it entails a whole pipeline from sampling to image annotation. So scientists like Sarah go out on research vessels to collect plankton in fine mesh nets at defined depth and well-defined locations. In particular here, the Terra Oceans expedition sampled plankton all over the world. And this is a unique collection which allows us to study diversity on a global scale. These plankton samples are then traditionally analyzed with a stereo microscope by taxonomists. That's of course very labor intensive, and you need highly specialized people for this. So the content of image data you can get out of it is constrained by time. Yeah. So we have this kind of trade-off between the quality, quantity, and time that we want to invest or get out of our imaging. And we cannot really replace this expertise in taxonomic annotation. However, the actual image acquisition can be automated, and the annotation process can be supported by automated predictions. And this also allows us that the annotated data can then be stored and reused, and that actually human bias can be reduced a lot. And Sebastian has contributed a lot to this development, which allows us to really collect image data from large amounts of cells and thereby really address their complexity and even derive statistical relevant data on plankton communities or even their ecosystem. What remains challenging is just simply the diversity of these kind of samples. So not only are we recording cells, but there's of course all sorts of objects floating in the ocean. And only a very small part of the living content is actually cultivatable for optimization of these sort of methods. And the image data itself is not very useful without a taxonomic annotation. And sometimes the same species can look very different in different life stages. Symbiotic interactions means that there can be more than one species per image. And yeah, I think these are the central challenges. And for the rest of the talk, I will focus only on the part how we come from imaging to an automated identification. So this is kind of the outline of the imaging pipeline. First, we take automated multicolor confocal microscopy images. From these images, morphological features are extracted. Based on these features, taxonomic classification is predicted, and this prediction is then validated by experts via collaborative curation. Let's start with the first step. To compensate for the relative slowness of confocal scanning, I've implemented a two-step adaptive scanning procedure. So first we take a fast 2D overview image, like the one you see here, of sedimented cells. This is then quickly analyzed in Fiji, and the high-resolution 3D scanning is only triggered in positions of interest. And what this position is really depends on the ecological questions we want to ask. So you see already this step requires a pre-selection. In the most simple case, I would scan any object that is detected, or one could filter for objects in a certain size range, or one could even filter for specific cellular features, let's say chloroplasts or a nucleus. So at the moment, this is done with handcrafted filters. But obviously, it could also be done with AI. For example, when we want to detect more complex morphologies or very rare organisms that could be hard to classify or that haven't been classified before. So yeah, that is work in progress. From the 3D images, morphological features are extracted. This has been realized by Luis Coelho. So after projection and segmentation, a collection of 480 numeric features from 2D and 3D is derived for each particle. This includes biovolumes, texture and shape descriptors, intensity distribution, overlap features. So the output will be a list of the detected particles, their derived images, and these morphological feature descriptors. Now, a crucial step for connecting the generated image data to its biological context is the taxonomic annotation. Only when the images are annotated, we can connect them back to the information that people gained with other methods and in other disciplines. Specifically, so usually species are sorted into these taxonomic classification ranks. And ideally, this would be how we would like to sort the image data as well. However, many of these ranks are actually still disputed. And the gold standard for classification is often still morphology. So with the morphology information missing, it can be difficult to really set up a proper rank for every species. Nevertheless, the classification that we use here for the images is based on this kind of 4-level hierarchy. I showed you the first 3 levels here. The fourth one doesn't have space. And you can see it kind of corresponds to the taxonomic lineage for organisms. But then for non-living or other particles, there's some kind of morphological type. So it's like a half taxonomic classification. The reference training set for this automated classifier contained a total of 18,000 objects, which were manually curated and then classified into this 4-level hierarchical framework. A random forest classifier was empirically determined to perform the best, balancing accuracy and computation time. Due to the scale of this project, we cannot afford more than a few seconds of processing per image. And you can see here the performance of this classifier. The prediction accuracy is estimated by cross-validation. It reached more than 80% accuracy at the finest level, the genus level, and even more than 90% on the phylum class level. And when you look at this confusion matrix, which plots the true categories versus the predictions of the algorithm, you can see these sort of boxes along the diagonal, which show that the classification errors are typically within the same broad taxonomical class. So the segregation into the main plankton taxonomic groups is quite reliable. But there's, of course, still room for improvement. To further evaluate the value of these 480 features we also computed a classification accuracy from reduced numbers of features. You can see this here. And interestingly, the accuracy improves a lot until around 200 features, and then continues to improve slowly until around 400 features. When we apply the same method only on the bright field channel, so without the fluorescence information, the same method resulted in only 56.8% accuracy. So the fluorescent labeling really adds value for detecting taxonomic traits. The method also provides a confidence score, so that can either be used to filter only for high confidence predictions, or the opposite, to focus on the weakest predictions, to either invest more curation efforts on the training, or of course to ask an expert for validation support on these. Which brings us already to the final part, the expert validation, where actually human experts have to look at the images again. For this we use a collaborative curation web application, which is called EcoTaxa. Here you can see a screenshot with some example images, the 5 channels plus an overlay. Ecotaxa is actually the largest database of sorted plankton images now, and it's really tailored for expert annotation and validation. So also as a layperson or the public can go and browse these images. It's quite pretty. But you, as a non-registered user, you would only see the validated images that have already been validated by experts and whose annotation is actually correct as far as we know it. For registered users, we can upload our image data. They're also similar to what I presented, machine learning and soon also deep learning tools implemented to help with an initial rough classification of the images. However, these are trained on grayscale transmission images, and you see there are currently 2 instances running of Ecotaxa, which focus on slightly different imaging modalities. The one in Villefranche is the main one, and it's maintained by Jean-Olivier and Marc. What's really important about this platform, this imaging platform, is that it allows us to connect the information that we have from our image data back to ecological metadata, such as information about the sampling or other physical parameters, and also to the taxonomic framework, which is developing in parallel. So there's a taxonomic framework for eukaryotes called UniEuc, which is based on genetics and morphology. And yeah, so all these different disciplines kind of are coming together via this platform, which I think is very nice. So there are some challenges remaining from my perspective. One is that we would often need additional semantics to describe images. While the taxonomical framework is already really nice, oftentimes for real research questions, we would want to detect additional morphologies. So for example, the same species might look very different in the juvenile versus the adult stage, or a free living form versus a symbiotic form of the same species might look different. Also, viral infections change the morphology of cells and play an important role in marine ecology. So to show you one example, here we have a viral infection over time. It's always the same species. It would always be classified as the same category, but it would be interesting, of course, to detect these kind of infections automatically. Yeah, I mentioned already that the detection of novelties and unknowns would be of particular interest, and this is something we will probably apply this method to in the future, because there are many undescribed species actually that can be quite rare, and you have to acquire many images to find one of them, which again is not really feasible when you do it manually. And some open questions are also if we can implement some sort of transfer learning between these different imaging modalities. So Romain, I was listening to your talk in the morning. I think the label-free predictions can be very interesting here to try and get some kind of intermodality classifier between the transmission-based imaging modalities and the fluorescence imaging modalities. Let's see, I'll look into it. And of course, a more direct connection to the genotypic information via fluorescence in situ hybridization would also be very interesting. So with that, I would like to summarize that automated high content microscopy enables us to study marine plankton at higher detail and throughput than ever before. However, the diversity is still a challenge. It's a challenge for labeling, for the image acquisition, for training and prediction of annotations. The manual curation of the resulting image data is not really humanly possible anymore, so to quantify and annotate this image data, we really need the support of machine learning and maybe also deep learning tools. But given this AI support, high content microscopy is an emerging tool to ask quantitative questions on the systems level in marine ecology. And with that, I would like to thank you for your attention and the many collaborators on this project for their work, in particular my supervisors, Colombo and Nathalie. If you have further ideas or questions, after this conference, please feel free to drop me a note. I'm happy to hear your ideas, and thanks a lot.
Okay, thanks a lot for that talk, Mary. Very, very interesting. We've got a number of questions already appeared on the chat.
Right, let me just come back to the other window.
I can probably paraphrase some of those. So Peter Davis is asking about whether you're seeing changes in plankton population around the world. Maybe he's suggesting in particular as a result of the shutdown of industry in the current COVID situation. I guess that might be a bit too soon to have sent out your survey ships to work that out, but is this the sort of thing you're looking at?
I think that would be an interesting thing to look at, but yeah, as you already said, the limiting factor here is often the sampling and not so much the imaging, but we could, we have a research vessel that can go out to the local waters, so every 2 weeks we are collecting samples in an ongoing time series, and yeah, that can be interesting to study that, to see if we see any change after April, March 2020.
Someone was also.
I can now see your questions. Yeah.
Yeah. Someone's also suggested a related one. This is can you see microplastics pollution in the water at the same time?
Yeah, that's not what we're filtering for. But there are abiotic structures that are usually just thrown out. I guess if somebody wanted to look specifically for microplastic, there's a surface staining that's based on PLL that allows us to see the surface structure of many cells. And yeah, then microplastic probably wouldn't have any nucleus, any chlorophyll.
Yeah. So that's what I was going to ask. What sort of staining do you use to look at these?
Yeah, I can actually show you exactly the protocol, I think. So here you see, do you still see my screen?
Yeah.
Yeah. So yeah, this is the staining. I mean, the many chlorophyll containing, many cells contain chlorophyll, so they are autofluorescent. Then this is a surface staining. This DIOC6 stains mitochondria and cellular membranes, and then for DNA we just use Fuchs. Yeah.
So
and the fifth channel is of course just the transmission channel.
Right. Okay. Someone else was.
Now I see a black screen again.
That's okay. Someone else was asking if Chris Woods asked if you've been trying these samples on commercial imaging flow cell cytometers, such as the Amnis image stream.
No, I haven't tried it yet. No, feel free to come over for a demo. It's beautiful in Brittany.
Yeah.
I mean, the one issue with the inflow imaging systems that I mentioned briefly is if they don't lie exactly in the focal plane and we only get a 2D image, then we have problems to really, many of these have tiny spikes, and then we have a problem to see the full morphology for the taxonomic annotation. So we really need 3D images of the whole cell to capture everything.
Okay, so Jeline Dixon was asking what the size range of cells are that you're looking at.
So confocal is best suited for anything between 1 and let's say 200 micrometers, I would say. The size range we're looking at for like the diversity kind of peaks between the 5 to 50 nanometer range. So this is what we're focusing on.
Okay.
Yeah.
I guess she mentions can you do bacteria and zooplankton? I guess bacteria can be smaller.
Zooplankton are starting to get bigger already.
Right.
I'm not sure you would need a resolution of a confocal for that. It depends on what exactly she's interested in looking at. Maybe send me an email if you want to discuss it in more detail. Bacteria, they tend to be quite small. I mean, again, there's a size range, but this is really tailored for the eukaryotic microplankton.
Okay.
And then you would have to adjust a bit the imaging properties. But the principles can definitely be applied to other planktonic groups.
Okay. Martin Kenny asks, have you considered using PCA to reduce the number of features you use for classification? It seems only saying.
Yeah, I'm reading the question. Yes, I think Luis has looked into that. I can't tell you exactly the results, but yes, it's something that I also thought would be interesting to see if we can reduce it to the most important ones, and then maybe speed up the processing this way. So maybe the 200 most important ones, where you saw that the curve was still going up very sharply.
Yeah.
Yeah.
Yeah. So I think, I mean, is it a case of this? Is the image acquisition taking you a long time, or is it the classification that's taking you the longest time? Yeah.
Both.
Both.
Both of them.
So you can run them in parallel.
So,
one doesn't get ahead of the other.
yeah, they are both long. Let's say, I don't know, for like these kind of 4-well, 8-well wells a day.
So there's another question from Miso Mitkovsky, which I'm not sure if everybody can see. It says, thank you for the talk. Have you considered other imaging methodologies such as FLIM or CARS?
Not yet. I mean, still confocal is kind of a.
I guess you really want to keep it. You want to try and make things as fast as possible. Some of those techniques are going to be generally slower, I'd have thought.
Well, I think in the future it can be interesting to look also at different modalities. I know that a lot of imaging is done with like SIMS and nanosims, where you can more look at metabolic exchange between cells. So there's not so much about resolution, but more about chemical contrast. FLIM, I'm not aware of. CARS, I'm also not aware of.
Okay.
No.
Okay. They give you can give you more molecular contrast.
Yeah, it could be interesting. Yeah. Well, we just don't have it available here at the moment.
No, I guess it's sort of are you trying to actually cite the micro